Hello, my dear friends. Today I'm going to explain what is a gradient of a scalar field or a scalar function. What it means? Because this question comes in mind that what about the gradient u? What this quantity is? Is it a vector quantity or is it a scalar quantity? And what this quantity physically represents? In a layman language, we speak about the gradient of any scalar field, like the gradient of temperature, or I say temperature gradient. Temperature gradient means how the temperature changes with respect to the distance, with respect to the space. But this is not the correct definition. This is partially true. This definition partially true. So spatial variation of any quantity, maybe temperature, maybe scalar field like the potential. When there is a variation in a space, then we are interested. What's the variation, what this value is, what's the numerical value of this variation, how any physical quantity which is a scalar, it changes in the space, how it changes in the space. And of course it changes in the space. Now in which direction this change comes out to be the maximum? We are also interested to find that direction also. In which direction that scalar field it changes maximum, and in which direction it changes maximum. So let's restart. What is the gradient of a scalar function? Okay. Dear friends, scalar field. So let there is a scalar field and denoted by u. And u is a parameter of x, y, z. Mean u is varying in the space. So we are having a scalar field. It is varying in the space. Like I am having a surface, a layer. Okay, the layer of which this is a surface, you call it surface number 1, and we are having some parameter like potential, and this potential is same everywhere on this surface. That's why it is called equipotential surface. U is not varying over the surface. U is same at every point, okay, on this surface. Right? But actually u is varying along the z-axis. Along z-axis mean like I consider another surface number 2, where u is different, and there is some increment in u. U is increased, the value is u plus du. But u plus du, but even this potential is also the same over the surface number 2. U plus du is everywhere on the surface number 2, it is the same. Now there's a point P and there's a point Q1, Q2 and Q3. So I have to go from P to Q1 or P to Q3 or P to Q2. So this is my choice. Like if I am going from point P, like I am going from point P to Q1, okay, then suddenly the potential changes from u to u plus du. But if we go from point P to Q2, even then change in u, it is the same. Or we go from P to Q3, even then the change in du, it is the same. So it does not matter like whether we are going along this path or going along this path or going along this path, because this layer having potential u, this layer having potential u plus du, everywhere it is the same and u is same everywhere. So hardly matters the path chosen. Okay, so we have chosen the 3 paths. Now u is a function of, already I explained to you that u changes in the space. So change in value of u going from surface or the layer number 1 to the layer number 2, how much the change it is. Okay, and how much change is du. This change is the same du irrespective of the path chosen. So the different paths are, the displacements are dr1 vector, dr2 vector, d3 vector. Now what we are interested, what is the change in du with respect to, what is the change in the, the scalar quantity, which may be potential, which may be temperature, right? With respect to the dr, okay, and moreover, it is a, the direction is also specified. But, there is a problem because the du, the change du, this is the same whether we are going along dr1, going along dr2, going along dr3. But this quantity, total quantity contains du as well as dr in the denominator. No doubt du is the same while going along the three different paths, but dr they are different in magnitude as well as in the direction. So if dr differs in magnitude and direction, that means total quantity changes. If we choose the path like this one or this one or this one, then this total quantity will differ. Okay. Now this du upon dr is called gradient of the scalar field, but this is again the partial definition. And what is the complete, true definition? Just we are going to that. So there are three different displacements, and du over dr in magnitude, it is in the denominator. Du is same, the change is same, no problem, but the total quantity will differ because in the denominator dr is in magnitude is different for the different paths. Now then what? Then we have to find maximum value of du upon dr. This is very important because it is related to the gradient of the scalar field. So maximum value of du over dr is called the gradient of a scalar field at any point P. Maximum value. So this is very important, the maximum value. So this is the complete definition, and it has a unique, then it will be in along a unique direction. That there will be particular direction along which the du upon dr will be maximum. So hence gradient of a scalar field at a point is defined as the maximum value of the spatial mean the spatial rate of the scalar field. How the scalar field changes with respect to space and along a direction where the change is maximum. Okay, and that is called the gradient of a scalar field. The gradient of a scalar field is du over dr and maximum and then the direction. So this is very important. The gradient of a scalar field is du over dr maximum, and r cap shows the direction along which this quantity is maximum. So gradient u is a vector quantity. It is having the magnitude as well as having the direction. So gradient u is directed along the direction in which the distance between the level surface is distance is minimum, mean if the denominator will be minimum, then the total quantity will be maximum. Since dr is minimum, therefore du or dr maximum. Okay, so grad u mean comes out to be the normal, just normal between the two levels, and that is the shortest displacement between the two levels when there's a normal distance. Okay, thank you. Now consider a coordinate system. Okay, x-axis, y-axis, and z-axis mean y in a space. This is a coordinate system, Cartesian coordinate system, and we're having the 2 points. P point having the position vector. P is having the coordinates like x1, y1, z1, and Q point having the coordinates x2, y2, and z2. And there is a displacement vector from P to Q. Okay, we are having a displacement vector going from P to Q. Let it is dr vector, and this dr vector is I cap x2 minus x1 j cap y2 minus y1 and plus k cap z2 minus z1. This is what the dr vector. I cap dx plus j cap dy plus k cap dz. This is a displacement vector while going from P to Q. Now we're going to derive an expression for the gradient of u in terms of the Cartesian coordinate systems. So again, the same according to our figure, these are the 2 points, and displacement vector already defined, like dr vector is equals to I cap dx plus j cap dy plus k cap dz. Okay. Now let u is any scalar field, and u is any scalar field such that u is a function of what it x, y, z. So u is varying in a space. U is varying in the space. Now the variation in du, okay, now I written the variation in du. Du can be written as I cap curly u by curly x plus j cap curly u by curly y plus k cap curly u by curly z. First of all, I'm going to explain this equation again. Now we are finding the total change in u. Total change in u is the sum of the change in the value of u with respect to x, with respect to y, with respect to z. First of all, how much u is changing with respect to x, and we to find the change when x changes with dx. How u changes with y per unit change along the y direction, and how much the y changes then. How u changes with respect to z, and what is the total change in z. So that becomes the total change in du. Now this whole expression can be written as I cap curly u by curly x plus j cap curly u by y curly y plus k cap curly u by curly z dot I cap dx plus j cap dy plus k cap dz. Because when you open the dot product, I cap dot I cap becomes 1, j cap dot j cap becomes 1, k cap dot k cap becomes 1. And when you open the dot product, you got the same expression as was written before, like this expression when you open the dot. So this expression may be written like this. Okay, this is the same expression. Now du is equals to, so this quantity, and then I cap dx plus j cap dy plus k cap dz is what? It is dr vector. Okay, and a vector dot b vector is what? AB cos theta. So in the above expression, there is a dot product, okay, and then dot product mean the first quantity in magnitude, second quantity in the magnitude, and cosine of the angle between the two vectors. And du upon dr becomes I cap this in this quantity. Dr is taken along this side, So this, there was dr. This dr is taken to the left hand side. And then dr taken to this side. Now this is the expression. Now we to find the maximum value of this factor, this quantity. Maximum value. This will be maximum when the right hand side is maximum. Right hand side maximum mean cos theta maximum, and maximum cos theta is equals to 1, mean theta equals to 0 degree. Okay. So maximum mean when cos theta will be maximum, and maximum mean how much? Cos theta equals to 1. When the cos theta equals to 1, then it is of the maximum value. So du over dr maximum mean I cap I cap curly u by curly x plus j cap curly u by curly y plus k cap curly u by curly z. Now this quantity on the right hand side having the direction, that direction along which the du over dr is maximum, the change is maximum. So gradient u, which is a vector quantity because the right hand side is vector. So gradient u is a vector quantity because along the right hand side there are I cap, j cap and k cap. So this is del vector u. The grade u is the del vector u. Del vector u is a vector quantity. Now we to prove that the grade u is normal, gradient u is normal to the level, to the surfaces, like the example which was considered before. So du equals to what? Du equals to, already explained this relation, okay? Du is equals to del vector u dot dr vector. Now over the equipotential surface, what it is, u is constant, and over the equipotential surface u is constant, mean du change in u is 0. Change in u is 0 mean du equals to 0 over the equipotential surface. When du equals to 0 over equipotential surface, then what about the dot product? So this when we remove the dot, then here comes the cosine of the angle cos theta. Then theta should be equals to 90 degree because cos 90 equals to 0. That means in that case this vector and this vector comes in perpendicular. Okay. So on a level surface, like the equipotential surface, u is constant. U is constant mean du equals to 0. So du equals to 0. So gradient u and dot dr vector becomes equals to 0 and angle becomes 90 degree. Cos 90 is 0. So del u should be perpendicular to the dr vector. So gradient u is perpendicular. Gradient u is perpendicular, is normal to the level surface. Okay, that's it is. Thank you very much.